Hi, and welcome to Hypothesis Testing 1 and 2-tailed tests. We'll talk about what that means in a minute. To start with, I'd like to try these two questions which recap what we've done so far. Okay, so I've started you off with the one on the left. I've defined the test statistic and the null and alternative hypotheses. All we then need to do is test this, whether it comes up 6 times or less. So we assume H0 is true, I should add. X follows a binomial distribution, and then we can see the probability that x is less than or equal to 6, and you should get 0.0576. This is greater than the significance level, therefore we would accept H0, there's not enough evidence. For the second one, I've left a little bit more off, so you'd have to define H0 yourself. And I was looking for this, it's exactly the same as before, but this time we're looking at greater than 0.5 because it's biased towards heads. So again, assume H0 is true. This time look at the probability that x is greater or equal to 20, and this time we're just inside the critical region, and therefore we would reject H0, the coin is biased towards heads. Remember, we could do this problem by finding the critical region in each case and then seeing if the numbers lie in it, but actually this method is quicker. Okay, how about this one? Have a look and see if you can have a go at it. Be very careful with this one because it's slightly unseen. Okay, the key thing going on here is that in this question, it says it's biased towards tails. And although we've then looked at the number of heads, that's important. So it's biased against heads. And that's meant when we've done H1, its P is less than 0.5. On this one, we've said it's biased towards heads, and that's why P is greater than 0.5. But here, we've just said that it's biased. So what do you think is going to happen? Okay, well done if you get this right. So same H0 as before, but here goes. Here is what happens with H1. Probability of getting ahead is actually simply not equal to 0.5. It might be greater than 0.5, it might be less than 0.5. So that's where the not equal comes from. Okay, new information here, but the good news is we're going to deal with it in almost exactly the same kind of way. All we do is we take the significance level, which is 5% in this case, and we split it up. So we split it up so it's 2.5% to the left and 2.5% to the right. And then it's exactly the same method, well, pretty much exactly the same method as before. So now actually I've done the same situation as the second example. So the probability that x is greater or equal to 20 is 0.0493, but this time we're comparing with 2.5%, and in fact we would accept H0. Kind of weird because a minute ago when we were testing that it's biased towards heads, we rejected H0, but in this case we're not testing that. So, you know, it is sort of an interesting situation where you're splitting the significance level, but the fact that you're doing you're looking just whether it's biased will come into it. Okay, so that was good. That was a lot of revision covered, as well as this new idea. So what do you think a one-tailed test is and a two-tailed test? Well, these first two are our one-tailed tests, and that is because so for this one, if I drew my binomial distribution, which would be perfectly symmetrical. Okay, I know there's 20 of them. I'm only going to like roughly draw it in. Then what I'm looking at is I'm looking at this bit over here, this left-hand tail, in fact, because I haven't really drawn it all, but it would keep going down to really close to 0. I probably should have carried it on there. And what we're looking at is the left tail, but overall it's one-tailed. If I do it over here with heads being potentially being biased towards heads, sorry, then I'm building it up and back down. And then I'm interested in this region over here. Again, we've got a tail coming on, it's going up and down. That's what we call a tail when it kind of goes towards 0. And again, it's one-tailed. Whereas in this last situation, we've again got a binomial distribution. And we are looking either side here and here. We're looking at both tails. That is why it's called two-tailed. So we just need to be able to distinguish when something is one-tailed and two-tailed. We treat it in a similar kind of way, but there's going to be a few extra bits for this two-tailed situation. The main thing is reading in the question. These bits I've highlighted in green, biased towards tails, biased towards heads, or just plain biased. But we'll do a couple more examples to get our heads around this. Let's play a little game called one or two tailed. So I've got some different situations, and I don't actually want you to calculate anything. I just want you to tell me where it's a one or two tailed test. Even better if you can write down the alternative hypothesis in each case. So I'm just going to show you the first three questions. You can pause the video and have a go at these. And then I'm also going to go down to the next two. And then a final one. So I'm going to go back to the start now and go through them, but hopefully you pause the video, had a go, and you can see if you agree with me. Okay, first question. So Jessica complains that the dice she is using is biased so that she is less likely to get a 6. Okay, the bias kind of looks at the two-tailed bit, but actually it then says less likely to get a 6. So I think the alternative hypothesis is going to be that P is less than 1/6, where X would be the number of 6s that we'd get. So one-tailed. Next one, Hassan complains that the dice he's using is biased, so he's more likely to get a 1 than any other number. He decides to test at the 10% significance level, etc., biased towards a 1. So in this case, it's again going to be one-tailed. And we look at the number of 1s that we got, and the probability we think for the alternative hypothesis is that P is greater than 1/6. One-tailed. Next one, bus journey. Okay, 80% journeys, the bus company claimed that it has made improvements to the service and the bus is now on time more often. So it's going to be one-tailed, and we think that P is actually greater than 0.8. Brad wants to test whether a coin is biased. Write down the null and alternative hypothesis that Brad will use, etc. Okay, in this case it says biased, but it doesn't talk about whether it's biased towards anything. So yes, this is two-tailed. We're just interested in P not equaling a half. That would be our alternative hypothesis, two-tailed. Next one, records from a school show that 2 out of 3 students got grades A to C in maths. In the following year, 16 out of 20 students get grades A to C. Okay, so we've got more than 2/3 going on. Does that mean it's one-tailed? Well, hold on. Okay, part 1, the head of sixth form claimed at the start of the year that the results would be different because of a new tutor team. Test is claimed. So actually for part 1, this is a two-tailed test. P is not equal to 2/3. But if we look at part 2, the head of maths claims this improvement is due to the appointment of a brilliant new teacher. Test this claim. So this is talking about an improvement. So actually in the second part of the question, we'd actually be doing a one-tailed test. Sorry, P is greater than 2/3. And finally, records from a well-known Division 1 football team show that 6 out of every 10 passes are misplaced. Following the appointments, okay, we've got 17 out of 17, 5 are misplaced. So that's gone down. The coach thinks that the extra passing in practice has had a positive effect. A positive effect. So before we had 6 out of every 10. Because it's a positive effect, then there's going to be less passes, And the first one is actually going to be p less than 0.6. So even though something's kind of improving, we're actually, our success here is to get failures. So we want less failures, essentially. So this one is going to be one-tailed. But the existing man just stated that there was no difference in the way the team were playing. So here, that would be us looking at a two-tailed test. You kind of need a bit more information here. Oh no, it says the claims and then it says about no difference, so I'm happy with that. Okay, how well did you get on? I think I got 8 out of 8. Hopefully you're happy with that little quiz and you can recognize one and two-tailed tests. Let's have a look at another question on this topic. So I want you to pause the video and try this one yourselves. Okay, I'm going to go through this question now. So the key thing is to highlight, I think, some of the important information. We've got that the ratio of, I think I'm going to highlight the whole thing, the ratio of non-vegetarian to vegetarian meals is 2 to 1. That's going to give us a probability. Then we've got a random sample of 10 people in Manuel's restaurant and only one ordered a vegetarian meal. We're going to be looking at a 5% significance level, and then we're going to test whether or not the proportion of people eating vegetarian meals in Manuel's restaurant is different to that in Enrico's restaurant. And there's your key piece of information that's saying it's two-tailed or not equal to. So, but now we set up the problem in the same kind of way. So the ratio of non-vegetarian to vegetarian is 2 to 1. That's going to be the probability of somebody picking a vegetarian restaurant in Enrico's restaurant is 1/3. And we're assuming that's going to be the same in Manuel's. This is our null hypothesis. And actually, it's that the probability of a vegetarian meal in Manuel's restaurant is 1/3. I've not said all of that. I've just said the key information. And then we're going with p not equal to 1/3. And I think it's a good idea to just write down then that it's two-tailed or one-tailed. Okay, after that, we've got the significance level. Let's just remind ourselves, because it's two-tailed, we're going to look at 2.5% either side. So let the number of people in the sample who are eating vegetarian meals be x. That means we assume h0 is true, and we get a binomial distribution. We're nearly there. We're nearly we're basically where we were before. We're going to find the probability that x is less than or equal to 1. We don't need to find the probability greater or equal to, okay, because we can see this is at the lower end. In this case, it's not a symmetrical distribution, but it's not. You need to be a bit more careful when p can be one extreme, like a really small or really big. But here we can see that it's just going to be less than or equal to. This just comes with practice, to be honest. So it's 1.04, and then we can say this. Sorry, that 5 was there because I was saying it was step 5, but I've got rid of the steps. So we can say that 0.104 is greater than this 2.5%. So there's not enough evidence to reject H0, and the proportion of meals at Manuel's is not different to Enrico's. Obviously, only having a sample of 10 means that you probably have to have had 0 for it to actually reject H0. But that's the problem with a small sample. You need a lot. You need a lot to an extreme essentially to reject H0. Anyway, that's the example. Hopefully you're happy with this, where the different bit comes from, the fact that we're looking at 2.5%, but apart from that, it's very similar to before. In this question, we bring together the idea of a two-tailed test, which we've already given it here, and the idea of a critical region. And there's one extra little take on it. The fact is, it says the probability in each tail should be as close as possible to 0.01, slightly different to what we've spoken about before. So I want you to try this question, and then I'm going to go through it. Okay, first of all, I would say that we're going to assume H0 is true, because we've already been given that. So x is going to follow a binomial distribution, 40, and then we're going to use our probability of 0.25. Right, now we need to be careful. Actually, they've already split it up. They've already told us we're looking at 1%, but it's going to be as close as possible to 1%. So let's look at the left tail to start with. But we are going to have to look at both this time. Okay, with our calculator, we can look at the left tail. We don't know exactly where it's going to fall, so I'd use the list function here. And maybe try the first few, 0, 1. Let's go up to 5. It's quite quick to do. All right, and we get some quite small probabilities. I can see for probability x less than or equal to 3, I get 0.0046, was it? Which is definitely less than 1%. And then less than or equal to 4 is 0.016, which is greater than 0.01. But actually, the key thing is, I'm not just interested in that now. In the past, we would have said that that means that x less than or equal to 3 is the critical region. But now I need to think more carefully, which is closer to 0.01. And in fact, it's this one again. You can see it's about 0.0054 away, whereas this is 0.006 away. So this will remain, well, this will remain the critical region, but we had to be that extra little bit careful. So critical region is going to be, and I should probably be really careful now because I'm going to get two critical regions. I'm going to not just say x less than or equal to 3, but I'm going to say 0 less than or equal to x less than or equal to 3. Let's look at the right tail. Okay, we'll go backwards. So now we're interested in where it crosses over to become 0.99. And here we go. So the probability that x is less than or equal to 17 is 0.9953. So that means in a minute we can work out the probability that x is greater or equal to 18 by doing 1 minus that. And we can do similar here, 0.9884. Okay, we get 0.00465. Which is less than 0.01. And then 0.01156. Which is greater. However, in this case, although in the past this would have been the critical region, x greater or equal to 18, because this one's less than, we're actually again looking at it being as close as possible to 0.01. Okay, so I circled that one for that reason, and I'm doing the same here. But this time it's going to be here. Even though this would typically be outside of the critical region, we're just making it as close to 0.01 as possible. That's just a slightly different take on hypothesis tests, because if you have like 0.01001, you're so close to that 1%, and so we just we make this comparison instead. Therefore, the critical region is going to be 17 less than or equal to x less than or equal to 20. And overall, the critical region is this. Now we could do an observation and we could straight away see if it was correct. Sorry, that should have been a 20. Brilliant. Whew, okay, quite a lot going on there, as we saw before with the critical region. And we've got this extra thing. I know I keep going on about it, but this extra thing to just be careful about. All right. Finally, write down the actual significance level of the test. So remember, that is the probability of rejecting H0 when H0 is true. That's what I mean by the actual significance. So it's going to be if we go inside the critical region when we shouldn't have. So it's going to be this 0.0046 plus this 0.01156. Yeah, because that's the probability that I go in the critical region to the right, and that's the probability that I go in the critical region to the left. So overall, the probability that I go in the critical region is these two added together. I've not rounded the other one as well as I probably should have. Okay, but I get it as 0.01616, which is 1.62% or thereabouts. There we have it. Another question on hypothesis testing. I hope you're feeling happy with this. Alrighty, that is enough examples. However, I just wanted to do one final video that gave a summary of hypothesis testing because we finished it for the binomial distribution. Okay, first thing you need to do is write down the test statistic, H0 and H1. Actually, we've typically written down H0 and H1, and that's been a probability in our case. And then the test statistic has been the number of times something has happened. So those are the things you should write down. H1 will determine whether you want a one or two-tailed test, and you can infer that from the question. In reality, it depends what you're interested in yourselves. Like if you're doing this in science later in life, okay, you get to decide whether you do a one or two-tailed test. But in A level, then it's going to be there somewhere in the question. Okay, you then need to specify the significance level, and that's going to depend on how confident you're going to be. If you're in an exam, it's going to tell you. If you're doing this later in life, then you kind of decide, but it's going to be, it's probably going to be around 5%. It depends on your field of study and how important it is to be sure about something. I've spoken about how 5% is unlikely and then 1% is very unlikely, for example. You then calculate probabilities using a statistical model. Actually, we've first assumed H0 is true and then kind of created the distribution. It's always been the binomial for us, but actually the same principle is going to work for any distribution, in fact. So just be aware of that. We've looked at hypothesis testing for one distribution, but actually the principles will apply for any distribution. We then find out whether the observed value of the test statistic falls in the critical region. The way we did this is one of two ways. We either found the probability and just compared it with the significance level, or we actually found the critical region itself. We've talked about kind of pros and cons to both of these. And then we state our conclusion. Is the result significant? Do we accept H0? Do we project H0? What are the implications? And give context to the original problem. So hopefully you're happy with that. If you kind of, if you saw that right at the start of this topic, you'd be like, what is going on? But hopefully now you're like, yeah. Hey, I'm back. Okay, so I don't know if you're ever like browsing the internet at say 10 o'clock at night and you just stumble across papers on hypothesis testing, but believe it or not, that's just what happened to me. So this is from the journal Methods in Ecology and Evolution, and they've got a paper from 2010 on hypothesis testing. And I'm going to throw this out there right now. I think that in all of everything you've covered in A-level maths, the topic that is most likely to come up if you just were to take any scientific article in the world, a scientific paper that is, it will be hypothesis testing. It's that important because every time we like decide whether a drug is going to be used or not, there's going to be hypothesis testing, and it's going to, it's going to go into all sorts of other things. I say medicine's a key thing, but this is on ecology and evolution, and they're writing about it. So there's lots you've seen in the questions I've given you, lots of different situations, and this paper talks about when we should use one-tailed hypothesis testing, and they just give some advice. I just thought it was quite interesting, really. So you never have to worry about this in A-level maths, but potentially later on you will. So they say, although one-tailed hypothesis tests are commonly used, clear justification for why this approach is used is often missing from published papers. So yeah, you should really say why you're using a one-tailed test if you decide to do that. Here they suggest explicit questions authors should ask themselves. I'm not going to get into that. We're not actually reading the paper here. We're just reading the summary when deciding whether to adopt it or not. And they suggest that they only use a one-tailed test if they can explain why they are interested in an effect in one direction and not the other. So if you can, you should really use a two-tailed test and say you're just looking for a difference. You need to be able to justify it. And to be fair, in a lot of the questions we've done, it has been justified because we've had maybe some evidence that, I don't know, a television channel is not being received as well as was claimed, and so on. Okay, they suggest a further requirement that adoption of one-tailed testing requires an explanation why the authors would treat a large observed difference in the unexpected direction. I came a bit lost with that one, to be honest. And yeah, I think that gets to the basis of what I wanted to say. Basically, you need to be able to give justification, and I think if you're not sure, you should go with a two-tailed test. There's a lot to it, I suppose. This paper is just one of, I'm sure, many papers on this topic. Hi everyone, I have one small little clarification I need to make on hypothesis testing after looking at the specification for A-level. Previously, when I've taught hypothesis testing, it's been on a different exam board, and they never actually referred to this quantity as far as I can remember. So there's something known as the p-value in hypothesis testing. And actually, I'm just going to jump straight, before I define it, the best thing to do is just say what it is. All it is this thing here. So when we did one and two-tailed tests, we looked at the probability that x was less than or equal to 6 at the end because that's how many times the observation came up. So that p-value is the probability that it would have happened through chance. We never called it the p-value, but we knew that we were calculating it. So where do you think the p-value is here? Well, there's only really one shout out, and it's going to be that one there. And then for the third example that we did on two-tailed tests, the p-value would have been again this one. Do you know what? It seems a bit harder to guess it for the two-tailed test because do I know whether I'm going to the right or to the left? So I suppose I'm not actually quite sure about that myself. It's the measure of the probability that an observed difference could have occurred by just random chance. The lower the p-value, the greater the statistical significance of the observed difference. I kind of think it's, yeah, so it's most clearly defined in one-tail testing. With two-tail testing, I think you just got to go with the lowest value. You're going to go with the side that makes the most sense. So just be aware of this because it will be coming up in assessments.